Right now, something we built is moving through a place no human instrument was designed to survive. It has been traveling for 47 years. It is 24 billion kilometers from the sun. It moves at 61,000 kilometers per hour, and it is not slowing down. Its name is Voyager 1. It has already crossed what scientists call the boundary of our solar system, but when it reached that boundary, when it crossed the line separating everything we know from everything we don't, the data came back wrong. Not approximately wrong, fundamentally wrong, and NASA spent nearly a year trying to explain it. Why this is not just a number. The heliopause is the boundary where the sun's influence ends and interstellar space begins. It is, by definition, where our solar system stops. If Voyager's data at that boundary doesn't match the model is incomplete. And if the model is incomplete, we don't fully know where our solar system ends. We spent decades drawing that map. Voyager 1 reached the edge of it. What it found there didn't match what we had drawn. A machine that was never supposed to last this long. Voyager 1 launched on September 5, 1977. It was built for a 5-year mission to photograph Jupiter and Saturn. Nobody seriously expected it to still be transmitting in the 21st century. It is. 3 radioisotope thermoelectric generators power the spacecraft, converting heat from decaying plutonium-238 into electricity. At launch, they produced 470 watts. Today, nearly 5 decades later, roughly 250. Every year, the output drops by about 4 watts. Since 2007, engineers at NASA's Jet Propulsion Laboratory have been shutting down instruments one by one to keep the remaining ones alive. The antenna Voyager uses to reach Earth is 3.7 meters wide. Its transmitter produces 23 watts, the power of a refrigerator light bulb. By the time that signal crosses 24 billion kilometers of space, it arrives as a whisper the deep space network's largest dishes can barely distinguish from background noise. It takes 22 hours and 35 minutes for that signal to reach us. If something goes wrong with Voyager 1 today, engineers won't know until tomorrow. Their response won't arrive at the spacecraft until the day after. One exchange, question and answer, takes 45 hours. At this distance, there is no rescue, no repair crew, no abort option. We can only listen, interpret, and send instructions into the dark, which becomes a serious problem very soon. The wall. We drew that was never really there. The sun doesn't end at a hard surface, it bleeds outward. It constantly releases charged particles, electrons, protons, helium nuclei, in every direction at speeds between 400 and 800 kilometers per second. This is the solar wind. It fills an enormous bubble of space around our star called the Heliosphere. Eventually, far enough out, the solar wind loses momentum. It slows, stalls, and collides with the gas drifting between the stars. The interstellar medium. The boundary of that collision is called the heliopause. Inside, our solar system. Outside, everything else. For decades, the heliopause was theoretical. We knew it existed, we just didn't know exactly where or what crossing it would look like. The models made clear predictions. As Voyager moved from the sun's magnetic domain into the interstellar medium, the magnetic field orientation would shift, measurably, unmistakably, as it entered a region shaped by other stars. It was supposed to be a clean crossing, a definitive line. It wasn't, and this is where things get strange. When the data came back wrong. On August 25, 2012, Voyager 1 crossed the heliopause. 2 things confirmed it simultaneously. Solar wind particle density dropped to nearly zero. Galactic cosmic ray density, high-energy particles from beyond the solar system, spiked sharply. Both matched the model exactly. But the magnetic field didn't change. The models predicted a clear shift in field orientation as Voyager crossed from the sun's magnetic influence into the interstellar medium, shaped by neighboring stars and the remnants of ancient supernovae. That shift never came. The field held the same orientation on both sides of the boundary. That's not what scientists expected, not even close. Ed Stone, Voyager's project scientist at Caltech, a role he had held since 1972, acknowledged the finding directly. The interstellar magnetic field near the heliopause was aligned with the sun's own field in a way no existing model had anticipated. NASA waited 11 months before formally announcing the crossing. 11 months of checking, rechecking, and ultimately accepting that the universe had returned a result nobody had prepared equations for. That shouldn't happen at the edge of everything. The boundary that kept moving. Voyager 2 crossed the heliopause in November 2018 from a different direction at a different point in the Sun's activity cycle with different instruments. It crossed at almost exactly the same distance, about 119 astronomical units from the Sun compared to Voyager 1's 121. 1 astronomical unit is the Earth-Sun distance, roughly 150 million kilometers. That match wasn't supposed to happen. The models predicted the heliopause would shift with the Sun's 11-year cycle. At solar maximum, when output peaks, increased solar wind pressure should push the boundary outward. At solar minimum, it should contract. The two spacecraft crossed at different moments in that cycle. They should have measured different distances. They didn't. But here's the problem. That wasn't the only thing that didn't fit. Voyager 2 detected something Voyager 1 never could. Its plasma science instrument, lost on Voyager 1 in 1980 when a stuck valve drained its calibration fluid, was still functional. It found a thin layer just inside the heliopause where solar plasma temperature spiked to approximately 50,000 Kelvin. That layer wasn't in the models either. When both crossings were examined together, the heliopause wasn't a line. It was a zone. Turbulent, magnetically tangled, shifting. Both spacecraft crossed it differently, at different speeds, encountering different internal structures. Tom Crimagis, who led Voyager's low-energy charged particle instrument team at Johns Hopkins University's Applied Physics Laboratory, said the spacecraft had not updated the textbook on the Heliosphere. It had rewritten it. The models had imagined a wall. What Voyager found was a shoreline, chaotic, shifting, far harder to define than anyone had built equations to describe. The solar system isn't where you think it ends. And there's one detail about Voyager 1 that completely changes how you see this. Pause on that for a second. It hasn't actually left the solar system. Even now, 24 billion kilometers out, 12 years past the heliopause, Voyager 1 has not left the solar system. The Oort cloud, the vast shell of icy bodies held by the Sun's gravity, stretches from 2,000 to 100,000 astronomical units outward. Voyager 1 won't reach its inner edge for another 300 years. It won't exit the far side for 30,000. The heliopause is where the Sun's wind stops. The solar system extends much farther. Diagnosing a dying machine across 24 billion kilometers. In May 2022, one of Voyager 1's 3 onboard computers began sending garbled data, long strings of meaningless numbers replacing coherent status reports. The science instruments were reading normally. The antenna was clearly still pointed at Earth. The signal was arriving at full strength, but the housekeeping data made no sense. It took 4 months of 45-hour round-trip diagnostic exchanges to find the cause. A single chip had malfunctioned, rerouting data through a corrupted memory location. The fix required rewriting the flight software in real time across 24 billion kilometers. Carefully, because the spacecraft's memory is so limited that a misplaced command could silence it permanently. They fixed it. In November 2023, a different computer failed. Engineers had to reconstruct accidentally overwritten code from 50-year-old documentation and transmit it back in fragments. That repair took until April 2024. Voyager 1 is beyond any form of physical intervention. Whatever breaks next, the only tools available are math, patience, and a 23-watt signal crossing empty space. If the edge is wrong, the whole map is wrong. The anomalies Voyager found haven't just raised questions about one boundary. They forced a revision of how scientists model the outer solar system entirely. The heliospheric current sheet, the vast rippling surface where the Sun's magnetic field flips polarity, was predicted to flatten and compress near the heliopause. Instead, Voyager found it forms magnetic bubbles in that region. Structures roughly 160 million kilometers wide, irregular and tangled, replacing the smooth transition the models described. The outer heliosphere isn't a calm frontier. It's turbulent in ways existing physics struggles to fully reproduce. And this is where it stops making sense. We have exactly 2 data points. 2 spacecraft, 2 directions, 2 moments in time. We cannot say whether what they found is typical or anomalous, because there is no third measurement. The deeper implication reaches further than boundary definitions. The heliosphere's structure determines how much galactic cosmic radiation penetrates to the inner solar system. That radiation shapes planetary atmospheres. It influences the chemistry of the molecular clouds from which solar systems form. If our model of the heliosphere is incomplete, our model of how solar systems interact with the galaxy around them is also incomplete. This is not a narrow technical problem. It touches the conditions that made planets like Earth chemically possible. We assumed we understood the container. Voyager found the container is stranger than the models assumed, and we've only sampled 2 points on its surface. What we sent with it. Mounted on Voyager, 1's exterior is a gold-plated copper disc, 12 inches in diameter. It holds 115 images of Earth, people, landscapes, cities, cells, atoms, greetings in 55 languages, the sounds of rain, wind, surf, and a mother's first words to a newborn child, 90 minutes of music, Bach, Beethoven, Chuck Berry, a Navajo night chant, a Peruvian wedding song. It was assembled in 6 weeks in 1977 under Carl Sagan's supervision on the possibility that the spacecraft might one day be encountered by something capable of playing it. That disk is now drifting through a region no model fully predicted, toward nothing in particular. At 61,000 kilometers per hour, in 40,000 years, it will pass within 1.6 light years of a star, called Gliese 445. It will not stop there. It will keep moving. In a universe 93 billion light years across, 24 billion kilometers is almost nothing. Voyager 1 has barely left the driveway, and yet it is the farthest any human-made object has ever traveled. It is closer to nothing than anything we have ever created. The slow countdown nobody talks about. The engineers at JPL estimate Voyager 1 can power at least one scientific instrument until around 2025. Some projections extend that to 2026. After that, power will be too low to heat the instruments. They will fail one by one. The shutdown won't be a single moment. It will be a slow dimming, instrument by instrument, until the spacecraft is still moving but no longer measuring. Then, at some point after that, the transmitter will fall below what the Deep Space Network can detect. The signal will still be transmitting. We simply won't be able to hear it. We won't know exactly when it happens. There will be no final message, no clean last transmission. One day the signal will be there. At some point it won't. And for a while, we won't be certain whether the spacecraft has gone silent or whether we've simply lost it in the noise. Voyager 1 will keep moving regardless. It doesn't need power to drift. The map was always incomplete. What Voyager 1 found at the heliopause was not what the models predicted. The magnetic field didn't shift. The boundary wasn't clean. The outer heliosphere turned out to be stranger and more turbulent than the equations had described. All of that arrived on a 23-watt signal stored on magnetic tape from the 1970s, from a spacecraft built for 5 years that has lasted nearly 50. Ed Stone spent half a century as Voyager's project scientist. Before retiring in 2022, he said what Voyager had taught him most wasn't any single discovery. It was that the universe consistently returned results more complex than the models assumed. That every time an instrument reached somewhere new, the models needed revision. That's not a failure. That's what science looks like when it's working. But it means this: Voyager 1 is now moving through a region we have measured from the inside exactly once, with instruments that are failing on a timeline we cannot fully predict. Whatever it records before it goes silent, we will have one chance to hear it. There is no second mission. Voyager 1 isn't just exploring space, it's crossing into something our best models didn't fully anticipate. And whatever it finds out there, in the time it has left, we may not even have the physics to explain it yet. Thanks for watching, and I'll see you in the next one.